All right, section 6.3 is about multiplication and division, in particular, of course, of rational numbers, since we're still in that rational numbers section. And the first thing that we're going to talk about is how we go about multiplying. And we've sort of talked about this in a general sense already, of course, is that we multiply straight across the top, we multiply straight across the bottom. I would like to illustrate for you why that works with a picture, though. While students may not be nearly as concerned with why this one works, it's still a very good feature for you to be aware of because it is a little bit different than the addition and subtraction features. So what I'm going to do first is to draw just a rectangle. There's nothing special about a rectangle. You could do it with other shapes. It does work nicely to use a rectangle. And what we're going to do is we're going to split the rectangle vertically into, we'll go with the first one, 5, into 5 boxes. Try to make them, roughly the same size. And if they're not, just know that you're not alone in not being able to draw. So what we're doing basically is we're drawing this fraction right here, 3 over 5. Okay? So I want the fraction 3 over 5, and I want then to shade in how many of these planks or block boxes? 3, right. So we're going to shade in 3 of these. This is the fraction 3 over 5. Okay, so imagine this is a garden, for instance. Maybe that would work. You've got a garden, and it's 5 feet wide, and you've got 3 feet in which to plant your tomatoes. I don't know, something. Okay. All right, now the next thing we're going to do is we're going to split things vertically. I'm sorry, I said vertically. We already did vertically. Horizontally into 4 regions. Why would I be using 4? Yeah, it's my second denominator. So 4 is a lot easier to split into 5s because you can just split it in half twice. So here's half. There's half of that one. I say it's easier. I'm lying. That'll work. Okay. Now I want you to sort of, for a moment, only consider your 3 rows of tomatoes that I just shaded in. Okay? If you have those 3 rows of tomatoes, so just cover up this piece right here. It's just not here at all. Okay? And you're looking at dividing them this way now. Okay? So you've got the 3 columns or rows of tomatoes, and then you're going to look at it sort of like here. So now you have 1, 2, 3, 4 rows, right? And we're supposed to shade in 3 out of those 4 rows, okay? So over here, you're going to shade in 3 of the 4 pink rows with some other color, if you will. So I'll use, well, maybe I'll use purple. So here's 1 row, here's 2 rows, and here's 3 rows. So let's take a look at what actually has happened. So you had the ability to plant 3/5 of the garden in tomatoes, but once it came right down to it, you only had the money to plant 3/4 of what you were able to plant. You had the ability to plant 3/5, but you could only plant 3/4 of that 3/5. The question is, how much did you plant? Well, you can count the boxes. How many boxes did you actually shade in with the purple? 9. How many boxes, if you will, total are in this entire diagram? There are 20. And you might be able to reduce this fraction, right? 9 over 20. Now this one, no, we're not able to, but you could reduce at that point if it were a fraction you were able to reduce. So this is, what does we say? Oh yeah, I have something written funny on my paper. Yep, good. All right, so this is 9/20ths of the diagram that you have shaded in. And sure enough, the way you get 9 out of 20 from this particular set of numbers is you multiply straight across the top and you multiply straight across the bottom. Okay. Does that kind of give you a picture? I recognize that this is kind of a complicated picture of what it is, but that's really how it works with the multiplication idea. All right, let's look at some properties of multiplication of rational numbers. The first one is the identity property. All the identity property said is that there is a number 1 such that when you multiply it by any ratio on either side, the left side or the right side, the ratio remains unchanged. It's the same identity property we had for integers. There's an inverse property. Now this is new. We did not have this until today. in this sequence of classes anyway. I mean, that didn't happen, okay? This is the first time it's introduced in your textbook. If you have a fraction, a over b, a rational number a over b, there will exist a number b over a that is a unique inverse, multiplicative inverse. It has to satisfy the condition that when it multiplies by the number b over a times a over b, that you get back the value 1. Now, there is a key sort of piece here that I want to draw your attention to. Do you see that this says non-zero? This will not work if you've got the fraction 0 over something, right? Like the number 0 is 0 over 1 or something like that. You can't flip that upside down because then you would get a 0 in the denominator. That's not going to work. You can also think about this as what number would I multiply this back by to get back to 1? And that's the idea of what we're doing. You can't do that with 0, right? I can't multiply 0 by anything and get back to 1. It doesn't work. But it works for anything that's not 0. So just for an example real quick, let me make one up. Let's say we had the number 5. What would the multiplicative inverse be for the number 5? 1/5, right? 5 over 1 becomes 1 over 5. All right. You have a distributive property. The distributive property over addition or over subtraction would be equivalent. It says that if you have a fraction or a rational number a over b times c over d plus e over f, then we have the ability to distribute the fraction through. So I have a over b times the first fraction c over d. I have a over b times the second fraction e over f. We had an addition property of equality in the last section, and we had this idea saying that if we had two numbers that were equal, they would stay equal as long as if I added something to one side, I added its equal value to the other side. The same works with multiplication. If you have two values that are equal, you can multiply one side as long as you multiply the other side by the same value. Okay, that's all this is saying, is that I can multiply by the same value on either side and the equality stays the same. Again, these are things we use a lot with equations, solving equations. The next one is a very similar property, but notice what's changed. How is this title different than the last one?
Inequality.
It says inequality. Inequality means those less than, greater than kind of symbols, right? So as long as there's an equal sign between them, it doesn't matter what number's multiplied by on the left or the right as long as they match. You know, it stays equal. If you have a symbol in between that's not an equal sign, that is, it's a greater than sign or a less than sign, we actually have things happen a little bit differently. In particular, what this is saying is that if we multiply by a positive number on both sides, the inequality stays the same direction. And if we multiply by a negative on both sides, the inequality changes direction. So notice right here, this is greater than symbol. This is a greater than symbol. Stayed the same direction. But when we multiply by a negative, the greater than symbol becomes a less than symbol. It switches direction. And you know this works. You've seen it happen multiple times. This is the idea that if I said, for instance, 1/2 is less than 4/3, which it is, because 4/3 is bigger than 1. So this works great. If I multiply by 3 on both sides, it's still going to work. If I multiply by 6 on both sides, it's still going to work. If I multiply by 2/4 on both sides, it's still going to work. It doesn't matter what I multiply by, the equality stays the same as long as it's positive. But if I multiply by a negative, and just for ease, I'm just going to multiply by -1 because it's the easiest one to multiply by. And I then get -1/2, and I get -4/3, the inequality, which originally was a less than, will now become a greater than. If you think about it from a number line perspective, what you're saying here is that the fraction -4/3 is on the left-hand side of the fraction -1/2, which is actually true. So 1/2 is a bigger number because it's further along the number line to the right-hand side. Bigger numbers are on the right-hand side of the fraction. So that's what that's saying. Multiplication property of 0. It says if you multiply by 0, what happens? You get 0. Yeah, you do. So that one's a nice, clean, simple one for us to remember. All right, so what we're going to do with these next is we're going to actually take a couple of equations, and we're going to work through the equations, solving them. Okay? So solving equations is about a 6th grade, 7th grade topic, so I know that doesn't apply to all of you, but it does apply to some of you. And so multiplying by equation, or multiplying these values to each sides of equations, we might be adding in particular problems, sides of equations and so forth. So we're taking a look at the number 3/4 x equals 1/5. So what would I need to do to get that 3/4 to move, to go away? Multiply by the multiplicative inverse, right? So the multiplicative inverse of 3/4 is 4/3. So what I'm doing right now is 2 steps in one. Number one, I'm using the multiplicative inverse property. That's where I got the 3/4, or the 4/3. I mean, that's how I chose it. And then I'm also using the multiplication property of equality. That's what allows me to do this and multiply both sides. So there's 2 properties that I used all in the same step. Now, when I actually multiply the 4/3 times the 3/4, technically that actually becomes the number 1. And this one over here becomes the number 4/15. So when I do that, again, I'm using, it became 1 because it's a multiplicative inverse. Okay, so in some sense I'm using the multiplicative inverse property again. So we could write that again if you'd like, the multiplicative inverse property. And then I'm also using sort of the definition of multiplication, right? I mean, that's how the 1/5 times 4/3 became 4/15. Multiply straight across, top and bottom. It might sort of feel like you're already done, but very technically, what we really wanted on the left-hand side was x, and we have 1x. Of course, what happens? I mean, x and 1, yeah, we can just drop it, so to speak. Basically, what we're just saying is we're actually multiplying it. What is 1 times x? Well, it's x, right? I mean, and what in the world gives us the right to be able to say that 1 times x is x? Yeah, that's a multiplicative identity property. Multiplicative identity property says that 1 times a number is the number itself. So 1 times x is x. Now, I recognize that normally we don't even see this step right here. We sort of just gloss right on over it, don't we? But it's really in there. You know, we really do actively participate in the fact that there is an identity property there when we do it. All right, let's take a look at a little bit more complicated one. Okay, maybe a lot more complicated. There are so many ways we could start the problem, so you guys are going to get to pick. What would you like to do to start this problem? Get the x's together. So you'd like to move all the x's to one side and all the numbers to the other side? Does that sound okay? Okay, is everybody all right with that? Yeah? All right. So if I want to do that, then I'm going to have to use addition and subtraction. Agreed? So these are some addition and subtraction properties that we're about to sort of employ. So one thing I'm going to do is I'm going to, and I'll write it this way, I'm going to subtract the x, the x over 6 to the other side. And then I'll use a different color, or at least I'll try to. And then I'm going to subtract the 1/4 to the other side. If this were spread out a little bit bigger, it would be a little bit clearer. But I'm not actually going to combine anything. I'm just going to rewrite what I've got here. So notice the whole point in doing this is that these add to 0 and, whoops, these add to 0, right? Those 2 columns become 0. So I'm actually going to write down then that I've got 2x over 3 minus x over 6 equals negative 1/2 minus 1/4. And believe it or not, we've done 3 properties to allow us to do that on that first step. So somebody give me one property that we've done. What do you see that we've done? It's not inequalities because this is an equation. This has an equal sign. Inequality is a less than or greater than sign. So we don't have inequalities. Okay, I'll get you started. Why in the world did we actually choose to subtract x over 6? Why did we choose that? But why did we choose that particular value, x over 6? Because, what did you say? It will zero it out. Okay, so that's the correct idea, but no, the language isn't quite what we were looking for. Do you remember why? We like to use cancel far too much, too. Just as problematic. In fact, maybe more.
It's just moving it to the other side, or you're doing the same thing on both sides.
Okay, let me ignore this, the x's and 6. Let's talk about the 1/4 for a minute. Maybe it'll come to you guys. Why did we subtract 1 over 4? You got it. It's an additive inverse. We picked those numbers on purpose because when they added to something, they zeroed them out or they canceled them out like you guys are getting at. It's an additive inverse. Now, we avoided writing it because it feels a little awkward when we do, but we actually also used another additive property. We used the additive identity. What does the additive identity say? That when I add something to 0, it equals the same thing. So like in reality, right here, we've got a plus 0 there, right? I mean, those two numbers added to 0, and we just flat out didn't even write it down, did we? We just automatically just moved right on past it, presumed that we'd already knew that fact already existed or whatever. But it's actually the additive identity that allowed that 0 to sort of disappear from the discussion. There's one more property that we used. It's perhaps the biggest overarching property that we used, actually. And we chose these things for certain reasons, but what did we do once we chose x over 4? Or, I'm sorry, x over 6? We added or subtracted it for both sides, right? That's the additive property of equality. The additive property of equality is what allows us to do that. It's what allows us to make a change in the equation by doing something to both sides with addition or subtraction, as the case may be. Okay, so there's a reason we're allowed to do that. There is a property in play there. That's the additive property of equality. All right, so our next step is probably going to be to combine some things, right? Which isn't a property of equality anything, but it definitely is an operation on fractions. So let's start with the left-hand side. What would you want to do to the left-hand side to be able to combine those together? Common denominator. What would the common denominator be? 6 would be a good one. So what would I have to do to get the first fraction to have a 6 in the denominator? Right. Oh, and I'm so glad, Devin, that you said top and bottom. To multiply the top and the bottom by 2, so it looks something like that, right? So this ends up giving me 4x over 6 minus x over 6. We'll actually combine them in a minute here. Let's do the same kind of thing on the right. What are we going to have to do on the right-hand side in order to combine those? Find a common denominator, which might be the number what? 4. So what would I have to do to get it to be the number 4? Multiply the first fraction by the number 2 over 2, or 2 on top and bottom. So that gives me negative 2 over 4 minus 1 over 4. Everybody get us so far? So what allows us to do that? Well, I mean, basically what we're doing is we're using properties of fractions or properties of rational numbers. The same properties we used back in 6.1 to reduce or to simplify or the same properties that we used to get common denominators. We can combine these now, right? What does this combine to on the left? 3x over 6. And on the right? Negative 3 over 4. Fantastic. We can do a couple of different things from here. Maybe we should say what we did right here. So this is just combining fractions or properties of fractions. We'll say combining since I already started writing it. You could say a definition of addition of fractions. And that's what it means to combine in this case. Okay, what could I do next? There's at least 2 different things I'm seeing. We could reduce, which will, I mean, at some point we're going to have to reduce anyway, so we might as well reduce here. Is that okay with everyone? What would we reduce? The 3 and the 6. How are we going to reduce the 3 and the 6? You're going to divide them both by the same thing. What value? 3. So if we divide 3 by 3, we get 1. What about when we divide 6 by 3? You get 2. All right, so this actually becomes x over 2 equal to negative 3 over 4. And what we did is we reduced the fraction, or you could say properties of fractions. What in the world are we going to do next? Again, we've got a couple options. We can multiply by what? What do you want to multiply? 2. Why 2? Somebody said it. That is the why. I mean, what allows us to do it. I didn't say that well. Yeah, this is the multiplicative inverse. And do you guys really want to write down 1x, or are we good to just write down x? Yeah? So, in essence, when we do the multiplicative inverse here, we're also doing the multiplicative identity, right? Because we're getting the number 1 without writing it down. And we're doing the multiplication property of equality because we're doing something to both sides. We're affecting both sides at the same time by multiplying them by 2. All right, so what does that give me as my answer? What is negative 3/4 times 2?
3/2.
Negative 3/2. And it's just multiplication of fractions. Either you can multiply straight across and reduce, or you can look along those diagonals and recognize that the 4 and the 2 have the ability to reduce from the get-go. Either of those. There's a lot that goes on when we solve equations. When you really start writing out all the details, there's a lot. Yes, Abby?
Could you just cross multiply?
You could, but then you're going to have to divide, so I don't know if that's going to be any easier. But yes, that's the second option. You could. Yes, yes. All right. A couple more properties for you. All right. Oh, we're moving into division, actually. Okay, division of rational numbers. So by definition, the division of rational numbers says that if we want to know what is AB divided by CD, and it equals EF, this will happen and work only if EF is the exact fraction we need to multiply by CD to get back to AB. And I know that feels and sounds a little bit awkward, so let me just write it in terms of numbers. And I'm just going to use whole numbers, although fractions is fine too. The reason, oh, I don't want to do 5. Why did I write 5? How about I write 6? The reason that 6 divided by 2 is the number 3 is because 6 is equal to 3 times 2. And that's all this says. The reason that we can take this division and we can get an answer is because this value right here times this value right here give me back the AB that I started with. It's what division means. It means what would I, sort of the missing argument, the missing piece to get me back to the original value. Now, the reality is that what I'm about to show you in 614 is what you were thinking I was going to tell you in 613 right there. The way in which we do division is that we have A over B divided by C over D. And it turns into a multiplication problem, right? Where we flip the second fraction upside down. So the C over D becomes D over C, and it turns into multiplication instead of division. You do have to have the fact that you're not dividing, of course, by the number 0. That won't work, obviously. Okay, but what I want to show you is the why, because it looks a little bit mysterious. I mean, really, why in the world should we be able to simply flip and multiply? I mean, that's nice and it's handy, but what's happening behind the scenes here? So let me show you, and I'll show you with a little bit of algebra. And we're going to do A over B divided by the C over D. And I'm going to write it instead of having it written as one sort of a linear one, I'm going to write it on top of each other. So division also is sometimes written like this. Agreed? I haven't actually done anything yet. I've just distributed it. I've displayed it in a different way. Okay. Well, I don't like to have fractions on top of fractions. They're usually called complex fractions, and that doesn't mean because they're complicated. That's just their name. Their name is called complex. And so kids are usually encouraged to not have fractions inside of fractions or decimals inside of fractions and so forth. So we want to sort of eliminate the fact that we've got a fraction inside of a fraction. Well, that means that what we can do in this denominator is if we do not multiply the denominator by its reciprocal, then it would be the number 1, right? The multiplicative inverse. But if I multiply the denominator of this big overarching fraction by d over c, then I have to multiply the numerator by the d over c as well. Correct? Sure enough. But then what happens to the denominator? It canceled. It became value of 1. I mean, that's the whole reason we chose it, right? And what are we left with? Well, we're left with a over b times d over c, which was exactly what we were trying to show worked. It's because of multiplicative inverses. That's why this works. And we're so glad it does, because it is handy. It's very easy to use. All right, I do want to talk in terms of concrete, like illustration as to why division by fractions is what it is as well. All right, so we're going to go back into whole numbers just briefly. 6 divided by 2. We're going to draw a diagram of 6 divided by 2, and there's two different diagrams we could draw. So I'd like for you to draw whichever one you think of. What would 6 divided by 2 look like in a diagram? Think about having 6 cookies, okay? Because it's about that time in the afternoon, isn't it, to have a cookie? Maybe it's just me. Okay, I've got 6 cookies. I'm going to draw 2 diagrams here in a minute, so I'm just going to make myself one more diagram of 6 cookies so I can show you the other one. Oh, that wasn't what I meant to do. That was. All right, first diagram. Somebody tell me, what did you do to split your diagram? What did you do to show this 6 being divided by 2? You split it up into groups of 2 or 2 groups?
I was thinking groups of 2.
So like this?
Yeah.
Okay. And did someone else split it differently?
I thought of 2 groups.
2 groups. And these are the 2 different ways to think about it. This is exactly them. So this one gives me groups of size 2. And this one gives me 2 groups. That's what the 2 is doing in the problem. I mean, I know we get 3s in there as well, but that's not the part of the problem I'm focusing on. Groups of size 2 are 2 groups. The second illustration is the one, the 2 groups, is the one that most people think of when they think about division. And so we say, well, of course I can take 15 people and split you up into 2 groups. I can make you into 2 groups. But how do you make somebody into half of a group? It feels very awkward to talk about half of a group, right? However, let's go back up to our diagram above, the first one that Shelby mentioned, groups of size 2. If these are cookies, could I have groups of size 1/2? Yeah, you just cut those cookies right on in half, right? Yes, of course you could. So if you take this diagram of your 6 cookies, 6 divided by 1/2, using this idea that's listed first on here, this one right up here, we're going to make groups of size 1/2, which means we're going to split each of our cookies in half. This is what happened when too many people came over and you didn't have enough food. You did not order enough cookies. You had to cut them in half. You had to cut smaller pieces of the birthday cake, those kinds of things, right? Okay, so when you do that, how many groups do you have here of size 1/2? You have 12. Whoops, sorry, I didn't mean the 12 there. 12. And in fact, you can therefore see that in a concrete example, this 6 divided by 1/2 did in fact become 6 times 2 over 1, didn't it? It really does. Because division by a fraction is really splitting it into a group that's a fractional size. Now, we can't do that in people. We can't split you into half of a people. I get that. But we don't need an argument for that, okay? I mean, we just want to talk about why in the world it does make sense, in some contexts anyway, to divide by a fraction. Absolutely makes sense to divide by a fraction 1/2. You just have to have something where you can have it in halves, or thirds, or fourths, or whatever you've got going on, okay? Okay. This is going to feel like a little bit of an aside, but we're going to very quickly see where it comes into play, so just bear with me. Definition of exponents. So if we have a raised to the power of n, so a is a rational number and n is natural. So natural numbers are numbers like what? What are natural numbers? 1, 2, 3, right? So you don't include 0. Natural numbers are the ones you start naturally learning to count with when you're little. No child starts out counting with 0. Okay, they get to 0 eventually, right? Because somebody says, I have 3 apples, and then you ate all 3 of my apples. How many apples do I have left? They don't start with the number 0. So we are talking about numbers 1, 2, 3, and so on here. Okay, so we've got exponents that are natural numbers, and we have a rational number base. Then if we have the value a raised to the n power, this is a multiplied by itself n times. A times a times a times a times whatever, n times. So the first thing I want to do is I want to go through with you, and I think you know most of these. You may have some of them switched around in your mind. That's a possibility. But we're going to go through the properties of exponents, and then I want to show you why they work. Okay? Because sometimes it's difficult to remember the property because you didn't really know why the property worked to begin with, and so you have an easier chance of confusing it. All right, so does anyone remember what happens when you have an exponent to the power times another exponent? I said it wrong. A number to a power times a number with the same base to another power. What do? You add the exponents. Very good. So if you know that you add exponents when you multiply, what do you do with the exponents when you divide? You subtract. Very good. Next question, number 3. How is 3 different than 1? What's actually typed on your paper? What is different about them? Yeah, you've got everything raised to another power, right? What do you see not there? Another base. You don't have another base with it either. So what happens when you have everything raised to a power or you don't have a second base? You multiply the exponents. And again, I'll show you why, but that is what you do. You multiply the exponents. 4 and 5 are incredibly similar. You have something, either multiplied or divided, that is raised to a power. Do you remember how you can simplify that? Yeah, it feels like you're distributing, right? So you're going to apply that power to each of the individual pieces. And it works if it's multiplied. It works if it's divided. Notice, it doesn't say it works if it's added and subtracted, does it? Because it doesn't work if it's added and subtracted. That's why it doesn't say it. This is definitely a key point. It is multiplication and division specific here. 6 is a little different. How are 5 and 6 different? Yeah, the negative exponent. So what does it appear, or what do you remember that the negative exponent does? Yeah, it flips the fraction upside down. So instead of having a over b, you're going to have b over a. And then you can distribute the power just the same. So it's, well, in fact, let me write it in 2 steps just to remind you. So you can flip it, that's what the negative does, and then you can distribute the power, which is what step 5 said we could do, or property 5. Okay, I want to show you why these work. You ready? Now, let me make one disclaimer. As I'm showing you why these work, I do not expect you to show me on every problem why they work. That's not your point, okay? You're expected to use the properties and use them liberally. I do not want you to hold back and try to do things a long, hard way. That is not the point of what I'm doing here at all, I promise, okay? What I want you to see, though, is that when that kid, and you're all going to have that kid in some class at some point, asks you why, even if you don't know on the spot, you can say, I've seen this before, and I can find out the answer. Okay? These are not complicated, but they're very confusing if you don't remember the why, to be able to explain the why. So let me show you. The first one we said was supposed to be addition, right? Yes? So let's talk about why. We're going to do a specific example. So this is not a proof. This is sort of an argument by example time. That's what I'm doing. I'm arguing for you. This works by example. So a to the third. What does a to the third mean? A times a times a. So this right here is a to the third. What does a to the fourth mean? Right, 4 of them, yes? 4 A's. So you take a look at this total and you count them up and you say, how many A's do I have? 7. So this is a total of a to the 7th. And how do you get from 3 and 4 to 7? You add them. It's really all there is to it. Okay. Next one. This one's supposed to be division, yes? I'm sorry, it's supposed to be subtraction, yes, from the division. Okay, so we're going to do the same thing. Y'all already told me that a to the 4th is A, and a to the 3rd has 3 of those guys there. So then what do? You reduce, yes? We're able to reduce. That's a property of rational numbers that we did back at 6.1. And we're left with a to what power? It's really 1. We don't usually write it, but I need to make the point here for a moment. How do you get from 4 and 3 to 1? You subtract. So yes, I did in fact subtract when I sort of canceled those factors. On number 3, we said that this should be multiplication, yeah? M times N. So let's talk about why. Well, you already told me a moment ago that a to the 3rd is 3a's. But raising something to the power of 2 means multiplying it by itself, right? So you have a times a times the same quantity again. And how many a's does that give you? 6. And how do you get from 3 and 2 to 6? You multiply. Okay, is everybody all good so far? Everything seem okay? Excellent. Next one, the one that we call distribute, right? We said it looks like that anyway. All right, so it's supposed to look something like that, according to the property when we're done. Raising to the power of 4 really means multiplying something by itself 4 times. Agreed? So it really means this. AB times AB times AB times AB. Now, back in Math 1, and most of you have had it, no, not all of you have, but one of the very first properties we look at there is called the commutative property. Commutative property means we can change the order of multiplication, right? 5 times 3 is the same as 3 times 5. So if we apply the commutative property multiple times here, we can move these A's and B's all around so that we have all the A's listed first and all the B's listed second. So this opportunity to switch things around, that is definitely the commutative property. And the ability to, of course, also just remove those parentheses as the associative property, by the way, as well. But when I do this and I rearrange them, I can count them up and I can say I've got, in fact, 4 A's and they're all together, so that's a to the 4th. Same thing with my B's. So this is a to the 4th, b to the 4th. You can't switch things around like that when you've got addition that's being multiplied. That's why there's not an addition property like this. This works even cleaner, really, for the division one, a over to the m over b to the m. You just have a over b times 4 times itself 4 times, like this, right? Well, you just multiply straight across the top, yeah? And then straight across the bottom. So you don't even have to really regroup anything to do that. All right, the last one on this slide says that this one should become b to the m over a to the m. And we're going to write this out a little bit like I did on the slide where I actually told you that it was the truth. We're going to write the negative 4 out as 4 times 1. So obviously negative 4 is 4 times negative 1. Our ability to separate it out and to write it sort of as a fraction or a value inside of another parentheses like that, we're actually using property number 3 to do that. Property number 3 in reverse. So we're kind of going from like this viewpoint to this one. I'm separating the m times n to b times m and then times n. That's what I'm doing. Okay. Now I can do that and I can use the property from above, property number 5, then to write this as a to the 4th over b to the 4th and a negative 1. We can do that. And then we can do exactly what we talked about before, is the fact that a negative exponent flips a fraction, right? So this would then be b to the fourth over a to the fourth, because it's a negative 1. It's a reciprocal, or multiplicative identity even, too.
Is there any way to explain why the negative, fraction goes, or is that just you just have to accept that?
There is, but let me do it after I show you number 7. Okay, so ask me again. It's Lacey, right? Ask me again after number 7 if I forget, okay? All right, so number 7 is going to talk about the fact that a to the 0 is actually equal to what? Do you remember? It's 1. And so I want to show you why it works. When we do elementary math 1, in fact, I did this with them just the other day. I told them, for right now, you're just going to have to take this as a fact, and we'll prove it later. So what I'm about to show you is an actual proof. Because I'm not going to put numbers in for m. I'm actually going to do an actual proof. So I'm going to start out with the number 1. In fact, you know what? I'm not. I'm going to start with a to the 0. Why not? We'll go from left to right. One way to get a 0 would be to subtract two things that are the same. So like if I had m minus m, right? Yeah, that would work. So then what? Well, how did I get to the m minus m? Well, if I had a to the m minus m, I could go back to property number 2. Okay, look back on property 2 that's in your packet there. Property number 2, if I go from the right-hand side to the left, it says that subtraction of exponents was the same as division, right? So I can write this like so. And what in the world is a to the m divided by a to the m?
1.
Well, it's 1. It's the same number on top and bottom, right? So this is the number 1. And I said I could have started with the number 1. I could work this argument from left to right or right to left. It doesn't matter. Yeah. Okay, let me do 8, Lacey, and it might answer your question that you actually had, but with a specific example, okay? All right, so this should be 1 over a to the m. And we might want to talk about why in the world does the negative, in fact, do that. Well, one way to understand why the negative does that is that how do we get a negative 3 exponent? Well, because it's 0 minus 3. Right? I mean, that's what negative 3 is. It's 0 minus 3. And if we kind of follow the pattern that we just did on number 7 above, we could then write that as a to the 0 on top and a to the 3 on bottom. And then we know that a to the 0 is 1 with a to the 3 on bottom, so that negative exponent did in fact put it into the denominator. Okay, everybody all right with that? Okay. Let's do some examples with this. Some of your examples have letters, like this one, letter A, and some of them just have numbers, like B. All right, so a couple things about the directions. It wants simplest form. Simplest form means that you'd only have one A in the problem, so the answer can't have A on top and an A on bottom in the end. Okay, so only one A, only one B, only 1, 2, or whatever the numbers are when you're done. And then the second thing it tells you is positive exponents. So if something is still a negative exponent, it needs to be moved somewhere else, and we've got ways in which to move it. Now there's several ways to do these problems, and there's several orders in which to do them. You might look at this and say, oh my goodness, I do not want the negatives in the problem, so I'm going to deal with that first. Or you might look at this and say, oh my goodness, I do not want A's on top and bottom. I'm going to deal with that first. Okay? So what would you guys like to deal with first? The negatives? Okay. So if you want to deal with the negatives, the only negative in this one is the A to the negative 3. So what would we have to do in order to deal with that negative? Move it to the top. All right, so this is already what we have on the top, and now we have this on the top as well. And what remains on the bottom is the B squared. Excellent. Now let's, hang on, I think I screwed something up, didn't I? Yeah, I did. Like, that's not right. I shouldn't have 3 B's. Is that better? Excellent. Okay, so now then, what you probably look at this and want to do is probably combine the A's, since there are 2 A's that are sort of by them, you know, both on the top right here and here. So how in the world am I going to be able to combine a and a cubed? I'm going to be able to add them. That's property number 1. That is a to the 4th. Very nice. I still have a b to the 4th on top, and I still have a b squared on bottom. And again, there's at least a couple of ways to think about what we're going to do next, but we're all going to do the same thing. That is, we're all going to recognize that we can't have the b on the top and the bottom. So one way to think about that is to use what could we do with the b to the 4th and b squared? We could subtract the exponents, 4 minus 2. What else could we do?
Multiply.
Yeah, we could think about it as though it's like multiplied out, right? I mean, like this really is 4 b's and it's got 2 b's in the bottom, so 2 of them are going to cancel out. Now, what we're not going to do is we're not going to say 4 divided by 2. It's not division. We're not dividing. Unfortunately, I've chosen numbers that don't actually show that very well. We're not dividing those exponents. We are, in fact, subtracting them, or we're canceling out b's. So if we subtract, I think that's probably my favorite at this point. I'm going to take 4 and then minus 2, and 4 minus 2 gives me squared. So this is a to the 4th b squared. And we don't end up having a denominator now on this one, which is fine. But we certainly could have had a denominator, and that would be fine too on a different problem. All right, so aside from the fact that part B has numbers in it and not letters in it, what else is sort of a little bit problematic on part B? Well, we're going to have to do something with the fractions, but there's something about them that makes them difficult. The denominators aren't the same, but then neither are the numerators, right, Devin? So right now, and in fact, you might look back at all those properties being able to combine things hinged on things being alike, right? The reason I could combine these a and a to the 3rd up here is because they both had a base of a. Well, I've got a 2 and a 5 and a 4 and a 25, and none of them are the same. I mean, they're not. But the question is, can I make them so that they are? And that answer is yes. So, taking a look at this, suggestions, anybody?
Can you flip 4 over 25?
We will flip the 4 over 25, but I'd rather right now, before we worry about that, get the 4 and the 25 to look like something else. Right now, we can recognize that this 4 is the same as 2 squared. And this 25 is the same as 5 squared. Right? I mean, I want them to look like the other number. The other number's smaller, so I have no choice but to move in this direction. I mean, I really have to take the bigger numbers and turn them into something smaller. There's not going to be another option the other way. So this is 2 over 5 to the 3rd. And for right now, I have 2 squared over 5 squared to the negative 6. Now we've got lots of things we can do after that. So somebody, do you want to, Rachel, was it you that suggested dealing with the negative 6?
Yeah.
Okay, do you want to deal with the negative 6 next? Okay, so you wanted to flip it. Is there anything else you'd like to do at the same time? Or do you just want to do the flip only? Can't add it to the first one, not yet. That'll be our very last step.
Take out the squared.
You could either take out the squared or you can multiply by the 6. Yeah. So I think maybe I'm seeing a lot of stares at me going, did she just start speaking another language? So I think we'll do it in 2 steps. So let's see. First you said to flip. So let's flip it. So that makes the 6 become positive 6. Is everybody okay with that? Okay, so our 6 became a positive 6. Instead of taking the 2 out, how about I distribute the 6 in? Will that be all right? Okay. So I'm not changing the first value. It's still 2 over 5 to the 3rd. But now I have, what do I have? 5 to the 12th over 5, I'm sorry, 2 rather. 2 to the 12th. The first one looks a little bit awkward because it says 2 over 5 to the 3rd. So how about we distribute that 3 in as well? Is that okay? So now I have 2 to the 3rd. And I'm going to put them into the same fraction because it means the same thing, right? I've got 2 fractions multiplied. So I've got 2 to the 3rd and 5 to the 12th on top. I have 5 to the 3rd and 2 to the 13 on top. 13, 12. Can't read my own handwriting. This is one of these ones where the process is actually harder with numbers than it was with letters. Okay, so now what?
Subtract exponents.
Subtract of what was that?
5.
5 to the third. Okay, so take these and simplify these pieces. Sounds good. All right, so you want to do 2 to the third stays the same, and you want to do 12 minus 3. Is that right? So this would be 5 to the 9th. Okay, so we just subtracted the exponents. Now what?
Subtract the exponents on the 2's.
Okay, so if I subtract these, what's going to happen?
11.
Yeah, we have one of two options. If we subtract them truly, by the way, the definition says we do 3 minus 12, which is negative 9. And then we can move it to the denominator. Or if we recognize the subtraction is going to put us into the denominator anyway, because the denominator is sort of bottom heavy, you know, over the fraction. The fraction is bottom heavy. We could do it directly there too, which would be fine. So this is perfectly acceptable as an answer. Another perfectly acceptable answer would be to write this as 5/2 to the 9th. Either of those would be perfectly valid.
Could you just in the beginning, instead of like making it negative 9, take the 2/3 from 6 to 12? Like you just leave it on the bottom.
Say it again. I'm sorry.
Like after we set the my part with the 5, hit the 2 stay on the top instead of taking the bottom, like taking 3 away from the 12, which would be 3.
Yeah, like doing, yeah. Yeah, you could do that way too, yeah. Okay, any questions before we move on from this one? Okay. We're going to solve equations now with exponents in them. And we're going to use exponent properties to do it. Okay? So in particular, our goal when we're working with these is to get the bases on both sides to match. So if you'll notice on part A, the base on the left is a 2. There's a couple of them, but it's a base of 2, right? And the base, if there even is one on the right, is a 64. They don't match. So the question, because I can't change the 2 into something smaller, it is the smallest thing, the question to ask yourself on the right is there any way that I could write 64 where it is a base of 2 to some other power? And you're welcome to explore that option by using your calculator. Exponents are integers anyway, so try it. 2 to the 3, 2 to the 5, 2 to the 12, 2 to the 8. I don't know. It's going to be 2 to the something. Oh, yeah, I do know. But it's going to be 2 to the something. So you may not know right off the bat, which is fine. So somebody find out for me, what number do I need to have it be in order for 2 raised to that number to be 64? It is 6. That is correct. So I'm changing the 64 into 2 to the 6th. How can I change the left-hand side so it has a single base instead of having 2 2's in there? Add them. So I've got 2 to the n plus 7 on the left, and I've got 2 to the 6 on the right. Now, it's going to look like I'm quote-unquote canceling the 2's. That is not what we're doing. We're not canceling anything out. But we are recognizing the fact that in order for these sides to be equal, if their bases are equal, their exponents must be equal. So it must be true now, since I have single 2 on both sides, that the exponents n plus 7 and 6 must be the same. And then we just did in the last little bit over here the ability to subtract that 7. So what does n equal? What is it? -1. You got it. N is equal to -1. And you could check it out, right? I mean, you could take your calculator and you could take 2 to the -1 times 2 to the 7th, and you can see that for in fact you will get 64. It will work. Okay. All right, B looks like it might be a little trickier for a couple of reasons. What's different about B? It's an inequality. That's one thing. What else? Somebody said there's a fraction, I think, yeah? There's a fraction. Okay, well, the goal is the same as it was before. The goal is to get the same base on both sides. And I would like to argue that 3 to the n doesn't get any simpler. I mean, there's nothing I can do on the left to make this any better than it already is. So the left-hand side is stationary, not to be messed with. The right-hand side, however, 81. Wow. So let's think for a moment. 81. How does 81 simplify? Yeah, there's 9 in there, and so I've got 3 to the 4th. But I don't really have 81. I have 81 in a denominator. So what am I going to have to do about that? I'm going to have a negative exponent. So the inequality is still here. That doesn't change, okay? But now I have 3, and it's negative 4 as an exponent. Okay, negative because the 81 was in the denominator, and then 4 because 3 to the 4th is 81. And again, the same property holds as I talked about last time. If the bases are the same, then the only way that this is going to work is if the exponents have that same relationship, in this case it's an inequality, that they already had before. So in some sense, I'm sort of ignoring the bases because they already match. And I'm focusing only on the exponents. So 3 to the n is less than or equal to negative 4. Any questions on that? I know this is a very, very long section, isn't it? It is. Okay. Oh, this is a nice one. This is good. Approximate. Approximate the following. 20 and 1/3 divided by 9 and 7/8. If you really want to calculate that out, man, you are stellar. That's awesome. But the approximate is a good thing to do. What would you do if you were trying to approximate this?
Down and then round up.
Yeah, so it would look like what, Rachel?
20 divided by 10.
Yeah, this is approximately 20 divided by 10, which is the value 2. So if we were wanting to find this exactly, and we ended up with an answer that said 32.65, we would know we made a mistake, because the answer should be approximately 2, right? That would be a rough estimate of what we should be getting. Here's a nice example. Jasmine is reading a book. She has finished 3/4 of the book. She might have done that, said that she knows that by looking at the spine. You know how you can look at, not the spine, but the pages themselves and say, oh, look, I'm about 3/4 of the way through. So imagine she did something like that. And she knows she has 82 pages left to read. So how many pages has she read? That's our question anyway. We could have flipped the question around and said something like, we know how many pages she's read, and then therefore how many does she have left to read as well. Same kind of thing. So what can we do? There's several ways to approach this problem as well. What do you see? 82 times 3/4. I don't think so. If the book was 82 pages long, that would be something we could do. Something else. What do we have? 82 times 3. Okay, so what you're recognizing is that we have 82 pages left to read, and 82 corresponds to 1/4 of the book. Does that sound like what you're thinking? Okay, so if 82 is 1/4 of the book, then how are we going to find out what 3/4 of the book is? Multiply by 3. Good thinking. So what is 82 times 3?
1046.
Now what if instead, we have to be careful we answered the question asked. We did. It says, how many pages has she read? But what if the question instead said, how many pages are there in the book? You could add that number back to the 82. Exactly. So word problems, you need to be careful about where the question's actually landing as its final ending point, not just kind of where it went to get to that point. All right. Another one. Al. Al's generous. Al gives some marbles away. Al gives 1/2 of his marbles, that should say to Bev. Bev gives 1/2 of these marbles to Carl. Carl gives 1/2 of these marbles, or these, to Danny. And Danny was given 4 marbles. How many did Al originally have? So we've got Al, and then we've got Bev. And then we've got Carl. And then we've got Danny. And Danny ends up with 4 marbles. So if we go backwards, I mean, I know she got those 4 marbles from Carl, but how many did Carl actually have given to him then? He had 8 given to him. But if he had 8 given to him, then how many did Bev have?
16.
She had 16 given to her. Then how many did Al originally have? 32. 32 marbles. And what you're doing there is you're actually doing exponents. You've multiplied by 2 multiple times, haven't you? 2 times 2 times 2 times 2. You did it 4 times. So that's where that's actually coming, or you did it 3 times. That's where that's actually coming from, is from the exponential property. Okay?